I expect my potential energy to decrease. Over here, if R gets bigger, does the potential energy decrease? Yes. Now suppose they were opposite charges. What will be the direction that Q2 is forced?
Negative J in this situation.
So the R between them will get smaller. But so now, if R is getting smaller, is my potential energy getting smaller?
No, it's getting bigger.
So what's the problem? Because I know the potential energy has to get smaller. And we just found the huge flaw that's going to unravel all of physics.
No,
Maybe a part.
there's a constant.
No, it's not, it had nothing to do with constant.
Oh, can't we throw in a negative?
Say it again?
Can't we throw in a negative?
What do you mean just throw in a negative?
You know, just,
What would that do?
well, it would make it to where when they're like charges, the math works out to where it's.
With their
R
opposite
still-
charges.
Yeah, where when they're opposite charges, the math works out to where R still gets bigger.
So we don't need to throw in a negative.
Well, not throw in a negative.
In order for this to be attractive, they have to be opposite charge. One of them has to be negative.
Right.
Already.
Yeah,
So this right here is, the numerator would be negative. I don't have to throw it in, it's part of the problem.
right, so then it gets smaller regardless.
Yeah. Because this is, if they're opposite charges, this is a negative number. And therefore, as R gets smaller, this will get smaller.
Or get more negative.
It becomes more negative.
Yeah.
Let's just work through some problem. Little bloody jug. 5 microcoulomb charge there, negative 4 microcoulomb charge there. What is the potential energy of this system?
Plug and shut.
Do we know what R is?
That probably would be helpful. Let's make it 8 centimeters. Micro 10 to the negative 6.
Negative 2.25.
Anyone else get that? I would take off 3 points for that answer.
Negative 2.25
Joules.
Well, do we need a direction to, or
No,
no,
it's
it's
a
not a
scale.
vector?
What's the easiest answer?
Zero.
Why?
Well, we can set, well, no, not zero, but we can set at one of the charges, we can set the potential energy to be zero, which means it's just gonna be the other charge.
The potential energy has to involve 2 particles, so you can't say it's, well, I guess you. You probably could get away with that. What I'm going towards here is, remember, I could, suppose, now that I know that answer, suppose I said my constant was 2.25. What's the potential energy now?
Zero.
The simple answer is 0. So if you see a problem like this without the additional restriction, you can get away with that answer. Now, if my intent was that I just forgot and I did not mean for it to be 0 there, well, the first time you do a test, yeah, you caught that, it was not my intent, but you saw it, fine. But I might go, for test corrections, you can't assume that. Or I could have also said, use of E equals 0 joules at R equals infinity, and that sets the constant to 0. What this number means, though, is that, given this assumption, is that if I have the 5 microcoulomb charge right here, it would take 2.25 joules of, let's see, it's coming in there. I would need to, if I'm moving the charge to here at a constant velocity, I would need to exert negative 2.25 joules of work in order to move it from an infinite distance away to here. My policy was I had to make sure I had the minus sign correct. Now, if I introduced a third charge, not that we need the number, but how would you solve it? Again, assume potential energy is 0 at an infinite distance away.
Trigonometry.
No. Remember, these are scalars, which saves us that hassle.
Well,
You would
we
just-
still need the new R though, right?
Oh, okay.
Well,
Talk me through the process of how to solve it for 3 charges.
so can you find the potential energy between 2 of them? And then,
Or can we just do the other
from
two?
there, adding the third charge, can we not set,
So we have that potential energy, then find what, that potential energy,
Yeah,
and then what?
add.
Or at that point, would you have to find the third potential energy also between 5 and 3 or?
Yeah.
Uh,
That's, you got 3 different combinations of 2 particles. So you find the potential energy, and then add them.
I think it's so much easier when you're not involved in vectors.
Could you not do -4, 5, or 7, 3? Does it not matter? Which combination?
You have to do all 3 combinations. You'll do the 5, -4, the 3, -4, and 5, 3.
Oh,
Did I misunderstand your question?
no, I'm saying it doesn't matter, like, if you do the 5, you said you have to do all of them regardless, all the combinations?
Yeah.
Okay.
And
So-
what if you had one in the middle then of the triangle?
If you have one in the middle of the triangle, then now you're doing that,
And all the
that,
outsides?
that.
Okay, so basically compounds like based on the orientation.
Not necessarily based on, it's just adding another one. Orientation is a little vague,
Even if you
there's no
added-
vectors.
Even if you put the point outside the triangle, you still have to do the same
Yeah.
amount of.
Yeah. Now, if I ask, what is the electric field at the center, or what is the force on a charge, then you have to bring it in the tree. Let's take it to the next step. If, let's sort of do a recap of what we have so far. Recap. We've done some vector stuff. And if we have 1 charge, then, we'll start out with 2. If we have 2 charges, we're looking at the force is the primary mechanism for analyzing a vector quantity with 2 charges. So we have the electric force, 2 is equal to K, Q1, Q2, R squared, R 2 half. If I have only 1 charge, I can't find a force, but I can definitely find an electric field. So for vector and one charge, I have the electric field. And the electric field from that charge is K Q over R squared, R hat. If we are dealing with scalars, and two charges, we got potential energy, electric potential energy. So use of E is equal to K Q1 Q2 over R plus some constant. So in my setup here, there's obviously a blank. So is there a scalar quantity that I can deal with if I have a single charge?
The electric potential.
So if we think about how we got from force to electric field is we just removed one of the charges, well, we can do the same thing over here. That electric potential, just K times the charge over R, officially plus the constant. This is known as the electric potential.
And then
What? Oh, we'll talk about units next. All right, what are the units, SI units for force?
Newtons.
The SI units for electric field? The SI units for the electric potential energy? So we had newtons here, we got rid of a coulomb or rid of charge by dividing by, so we get newtons per coulomb. So over here, what would the units be?
joules per coulomb.
Now, for some reason, newtons per coulomb they could handle that, but joules per coulomb, that's way too much. So they came up with a single unit for it. The unit is the volt. Named after? Volt.
Volt meter.
This is one of the few units that, it is named for somebody, but it's not exactly his name. It's Volta.
Volt
Mr.
letter.
Volt. Mr. Volta to his friends. Now, the symbol for this is indeed electric potential, as was stated. And the symbol for electric potential, unfortunately,
It's also.
is the capital V. So we now can find a situation here where if I wrote V equals 5V, in math class V would be 0, but in physics this means that the electric potential is 5 volts. Those two V's do not stand for the same thing.
Wow, that's
No, we ran out of letters.
Yes, we need more.
We have only 100 letters if you count uppercase, lowercase, Greek, and our alphabet.
I think we need to start adding other
Sanskrit
languages as
or
well.
something.
Yeah, start adding, Sanskrit has a lot.
Or Arabic.
Or Chinese.
From Lord of the Rings.
You know, you can just
Ooh,
make
that
up
would be
new
interesting.
letters.
Yeah.
There probably are enough Tolkien fans in the physics community, so I said I'm happy with it.
Combine the letters into one letter.
Now, I have not talked about voltage yet. All I've done is identified volts and electric potential both have the V in it. Voltage is not far behind, but we have not talked about voltage. Any questions up to here before we talk about voltage?
Wait, so is there a way to deal with the fact that we have V as the electric potential and the unit?
Typically, the unit comes right after a number.
You don't have to write volts out or something.
Just understood from context,
So, assuming,
or supposed to be.
so based off of what I've seen so far,
Yep.
the way that we did electric field problems in 152, not how we played the game in 252. But the way, so I'm assuming same kind of thing with the way that we're gonna do these electric potential problems. Are we gonna start using calculus here? Or
At some point, we'll be using calculus.
with the
I
electric?
mean, we still have the same old problems that you had in 152, but
The method.
we can now start dealing with distribution of turn. And I know you're all anxious to do a distribution of turn problem.
For voltage.
Yeah, find the electric potential, not the voltage.
Oh.
So let's talk about voltage and this relationship to it. All right, so if I have a marker that sucks, and one that I can't use. All right, so if I have let's just say that the electric potential at this point is 7 volts. Because there's some charge distribution, it's 7 volts at that spot. And at this point, it's 5 volts, at this point, it's 3 volts, at this point, it's 2 volts. If I start at the 7 volt mark, and I go to the 5 volt mark, what is my change in electric potential?
-2.
Yeah, don't forget the negative. If I start at the 7, and then I start moving around, and end up there, what's my change in electric potential?
-2.
Still the same. The path does not matter there. It's just I got the potential in one spot, potential in another spot, final minus initial, boom. This is write it out, the change in electric potential. Or we go to 10:45, 10:50. Also known as the electric potential difference. Also known as the voltage. The voltage is the change in the electric potential. There was a test years ago where I set up a situation and I said, what's the difference in the potential between 2 spots? And then the next question was similar to, what is the voltage between those 2 spots? And it's just a matter of testing, do people recognize that voltage and potential difference are the same thing? Unfortunately, not everyone saw that it's the same thing. So what we have now gotten into is we have set up a mechanism so we don't really know what the electric potential is at any particular spot. But what we really care about is the difference in the electric potential. If I have a 12 volt battery, and I don't know if any 12 volt batteries ever come in this shape, but we'll pretend. If I have a 12 volt battery here, what that is saying, that's my negative end and my positive end, is it says the potential difference between these is 12 volts. My voltage is 12 volts. I'm not claiming that what the electric potential is here or here. All I know is that if that's 0, that's 12. If that's negative 12, that's 0. Because of that constant, the actual number here is irrelevant. What really matters is the difference. So we're setting up that with electric field, I don't really have to care, I don't care what created an electric field, all I care about is there's an electric field and how the particle is going to respond. I don't need to know what the potential energy is in order to figure out how particles are going to move, I just need to know what the potential difference is.
So is that like if you had a battery like that went from 0 to 12, and then one that went from negative 12 to 0, they would have the same effect?
Yes.
Okay.
So we're now also left with that situation of, if I have a setup like this, where 2 volts, 3 volts, 5 volts, 7 volts, and I put a positive charge here at the 5 volt, which way will it go? So 2 people have voted for left. The answer is either left or right.
Say that question one more
It
time.
has to be.
What's the question one more time?
The question is, if I have, let's say, let's set it up slightly better than that. I have equipotential lines. And I'm just gonna arbitrarily make that 7, 5, 3, and 1 volt. I put a positive charge on the 5 volt equipotential. Which way is that positive charge going to move? So there's 2 charges, 2 votes for the left and 1 to the right.
Right.
Okay, 2 against 2, 3 against 2, 3 against, oh, you changed your mind? Wait, physical like democracy?
Remember me.
All right, so Nick, you're now saying to the right?
Yeah.
Anyone want to say to the left? No, you changed your mind again? All right, let's think about this a little bit differently. If my formula for electric potential is KQ over R, let's assume that it's equal to 0 infinite distance away. If Q is positive, will this quantity get smaller as R gets bigger or R gets smaller?
Gets smaller. As R gets bigger.
As R gets bigger, it will get smaller. Okay. Yeah, since this is gonna be fixed for whatever the charge is, R will get, as R gets bigger, the fraction gets smaller. So since it's getting smaller in that direction, that means that I would have some sort of net positive charge over here. So the positive charge, this positive charge would move that way. Regardless of, what's creating it. If I put a positive charge here, and I know it's a lower potential there,
It seeks the lowest potential.
when all of this stuff was developed, they had no idea what charge was, but Benjamin Franklin said, well, let's